Great, thanks. Thanks for the introduction, and thanks for the opportunity to come on this virtual platform and have a chat with indeed a long-standing community. And I do look forward to the opportunity where we get to meet all in person again, hopefully at next year's ICBO. Yeah, this talk that I prepared today is a bit of a reflection about some of the current work that we've been doing, in particular the use of AI in support of data curation and ontology engineering. And also a little bit going back to the fundamentals. So I'll be talking a bit about the role of upper level ontologies and semantic interoperability. And I hope that it will spark further discussion for us to think deeply about how we go about doing this interoperability work. So normally semantic interoperability is really about how different systems, organizations, and agents can exchange data with an unambiguous shared meaning so that the information received is interpreted as it was anticipated, right, by the sender. More practically, from our perspective, as we are all data workers, what it means is that if you get a piece of data from one group or one individual or one format, and there's another representation for that, then we can find that they are equivalent, semantically equivalent, even though they are syntactically different and labeled differently, but their intention is the same. And so we should find their equivalents. So semantic interoperability really requires that we be able to map the data that are represented in these different data sets and formats to a shared ontology. That is a shared conceptualization and formalization of the domain so that we understand and can integrate data, we can reason about it, and we can generate inferences and answer questions and so on. So obviously, as one of the co-founders of FAIR Principles, this is a key part of the interoperability in FAIR, and that it will promote reusability by reducing the work that data workers have to do in order to find the correspondences between what are otherwise equivalent elements. That it helps us do this data integration across a wide set of different data sources and enable us to answer questions or to build predictive models. And it supports, the general scientific knowledge development and reuse of our data assets. And of course, from the perspective of health data, this is a huge problem, is interoperability across different data formats and different standards could be achieved. And that means that if you are in the US or in Japan or in Europe or wherever it is, and however the data is being collected about you can be transformed into a manner that's usable in a different system. There are lots of challenges that come with semantic interoperability, and I think I'll cover in this talk a little bit about these three levels: the heterogeneity that we see in clinical data, in clinical study data and observational studies, and also in prospective clinical trials. We define data dictionaries to collect information about patients in a particular way, and there is extraordinary diversity in the naming and the meaning, the encoding of clinical variables and their value sets, which don't align really well with pre-coordinated expressions. And so even though you can have really large ontologies such as SNOMED or ICD or what have you, Mondo even, not all possible expressions are there. And so sometimes you need to construct an expression for a particular data point, and you need to have that vocabulary to do that. So here's one example of a real world a variable that we have to deal with. It's heart attack, main cause of hospitalization measured at baseline. Categories, or the answers are 0 for no, 1 for yes, and 9 for missing, right? This is, we see this encoded data, and this is what the interpretation is for that. In domain ontologies, they offer an expansive set of categories of classes and properties to construct definitions. We see this in SNOMED, for instance, or in Mondo. We will have main classes, and then we'll have predicates that allow us to construct expressions to describe the membership of this class. But often these the classes as well as the relations are really constrained, or they're tailored, let's say, for the domain, and they fail then to cover situations or data representations between that domain, and that obviously poses a problem if you start collecting data for consumer electronics. Maybe you have elements of environmental or geographical information, and so on and so forth. Then you can't just use one ontology, right? You end up having to create an aggregate of ontologies, and you start piecing them together. But sometimes they have overlapping definitions or slightly misaligned definitions, and it becomes extremely difficult from a data use perspective to understand like what is the intention and meaning of these classes, as well as the relations that are there. And then finally, schemas are really important tools in data exchange. They allow us to indicate here are the data elements that we want, and this is the relations that we expect you to fulfill. And there will be cardinality restrictions, value set restrictions, and so on. But each of these schemas tend to be developed in a manner that is completely incompatible with any other schema. And so this creates all these different data formats that are fundamentally incompatible. And that means as a data user, you can't just integrate your data, even though they're conformant to different schemas. And I think this is a huge problem. So in this talk, I want to cover kind of three main topics. I want to tell you about our work in using language models to assist in the mapping of data dictionaries to standardized codes. I will tell you also about, I think, our work on trying to provide a common semantics across different domain ontologies as well as schemas as a form of conceptual and semantic interoperability. And then some emerging work, some ongoing work about data transformations and how we can use these mappings to upper level ontologies to directly transform from one data standard to another. So yeah, the first challenge is really, we have a number of projects that are targeted towards the use of observational data as well as, prospective clinical data. And as part of that, workers, typically have some kind of spreadsheet and have these data dictionaries that indicate what it is that they're collecting and the manner they're collecting it, the time at which they collect them, and all kinds of qualifiers, let's say, to that observational data. These clinical trial data collection often follow standards like CDISC standards, but observational studies might use different standards, such as OMIR. They differ in their table structures, their naming of the variables, the way in which we normalize or represent the values, and also the way that we associate it with a standardized code or standardized vocabulary. So that's one of the challenges, is like, depending on who collected it, you get a different format of that data, and they're not inherently compatible with one another. And then at the second part, you get the use of different terminology and coding systems, and they're not equivalent necessarily, right? So the correspondences between classes, let's say, in one terminology versus another, could be incomplete, or it could be ambiguous, or it could point to you could have many mappings, you can have a single one, or it could also be erroneous, and mappings are often revised and so on. So there are huge problems in you can't just assume just because you use one coding system that you'll have a compatible code in a different one, and that certainly creates a problem in terms of trying to extract information out of integrated data, let's say. So this has enormous impact on the reproducibility of our research, right? Depending on which coding system that you used and vocabulary, and the kinds of queries that you do, the aggregation tasks that you might have, the statistical analyses, you may get different results based on that. We also face issues in terms of using these data in clinical decision support. We don't necessarily have the degree of specificity that might be needed to understand the patient condition nor what was performed on them. And ultimately, for data workers, right, it reduces our productivity as we spend time trying to understand what people have done and the data they represented, as opposed to asking and answering the scientific questions that got us there in the first place. Okay, so let's take a few, just to ground this a little bit, let's take a few examples. So here's an example where you might see in a database, a data file, pmol/L, and this should represent the concept of picomole per liter, a unit. In SNOMED, it's considered to be a qualifier value. In CDISC, you also have it as a unit, and there's another ontology, UCUM, which also provides this unit definition. This is pretty straightforward, right? Because you have a lexical match, and conceptually, it's relatively easy to find these exact matches. There's not too many other meanings of this expression that you might find. On the other hand, you have more complicated or sophisticated clinical data elements, such as heart rate measured in the recumbent position. And if you were to do a search, so you use resources like Athena, and you try to find concepts that the OMOP community would encourage you to use, you will find hits, let's say, to something like heart rate taken in a specific position, right? That sort of matches the intended meaning here, but there is no heart rate measured in the recumbent position. So that concept doesn't exist as a coordinated expression. But, SNOMED has this other descriptor or a qualifier here, recumbent body position. And so what we really want to say is the meaning of this particular clinical data element is a conjunction of these two things, right? So you need to find in composite CDs, there will be a number of different matches for different parts of the expression itself. And then finally, you have something like, for instance, severity gradients. You have a concept here like mild to moderate asthma exacerbation. And when you do a search on Athena, you'll see a variety of different hits. And again, none of them are quite the same that you're looking for. That first hit is mild to moderate equine asthma. That is not what we intend to know. We want human. The next one is a moderate acute exacerbation of asthma, but it doesn't have the mild to moderate. Then you have exacerbation of mild persistent asthma, but that's not really the qualifier that we're looking for, and so on and so forth. And you even have the mild to moderate. So you see acute asthma and you see mild to moderate, but again, you don't see exactly the term you have. And I think a lot of data curators that are have this onerous task of trying to map the terminologies that they have available to the data that they're collecting are facing these problems endlessly, and they're enormously confused by the breadth of different terminologies that are available that might be there. Many of the things are not quite exact matches for what we're looking for, and they ultimately have to construct a kind of definition. Now, there have been many methods that have been developed to try to satisfy this concern, to aid in the mapping of concepts to, for instance, clinical data elements. There are rule-based systems and language model-based systems, and all of these struggle with especially the complex composite CDs that require an understanding of the context in which those data are collected and the relationships involving multiple different kind of qualifiers or attributes or contextual information. Large language models have also increasingly been applied, but they often lack the specialized medical domain knowledge unless they've been fine-tuned on medical data or augmented with domain-specific resources. They also face issues with scalability. Many of the approaches, they face challenges in processing very large controlled vocabularies, especially when they involve some kind of retrieval augmented generation approach, in handling overlapping and variable granular concepts, and typically have to align to some predefined schema for the construction of the definitions. Efficient scaling remains a critical challenge for real-world healthcare applications. And then finally, generalization and limited training data. Most concept linking methods struggle with generalizing to unseen data and exhibiting decreased accuracy due to limited training data sets. These require more robust models than we currently have. So what we have done is we built a new framework for doing concept mapping. It's called the CDE mapper. And it's intended to overcome challenges in standardizing these especially complex clinical data elements and those with varying representations. We use language models coupled with retrieval augmented generation to align these clinical data elements that we see in the cohort data collections with our controlled vocabularies. The pipeline makes use of basically a query decomposition, a phase where we break down these complex expressions into sort of individual elements that ultimately then we do try to find best matches for them in the databases. We generate we identify candidates and do some filtering on them, and we use LLMs to help us do ranking of the candidates and compose the ultimate expression. Okay, so we'll work through it here. So in the first part, the query decomposition, we use an LLM to decompose the query into structured output upon which the individual concept mappings are performed. We're using context learning with the original query, a description of the task, and relevant examples. And the LLM is instructed to attempt to identify the components of these that align with the format, which will be elements, what we call the base entity, associated entities, the value sets for which the data can be encoded, some element of the reference unit of measurement, elements of the patient, of timeliness, and also of methodology. Okay, so for an example like this, we have our first example of a heart attack may cause hospitalization, measured at baseline, and categories include 0 for no, 1 for yes, and 9 for missing, would populate this JSON-based structure as I show you here. Okay, so the next step is basically for each of these elements, we want to try to identify concepts or classes that we have in the database and try to retrieve them to be most accurate as we can. So for each decomposed query, the knowledge retriever checks the knowledge reservoir for an exact match. And this knowledge reservoir is a human validated database of LLM generated concept mappings. So every time we perform this task, we get candidates, the curators will evaluate and modify these mappings and then store them for future use. If the component is not found, then the knowledge retrieval occurs using an ensemble embedding retrieval strategy. We use a model called SPLADE for sparse representations for exact concept matches, and SAPBER for dense representations to discriminate between subtle variations. The concept embeddings are generated from the concept label, its synonyms, along with the hierarchical information and semantic type. And we search the query then against this embedded concepts to generate a ranked list. We use what's called a knowledge filter that applies a similarity threshold and metadata-based filtering to enhance the accuracy and precision by discarding this noisy, irrelevant, or semantically misaligned candidates. And we use a two-step re-ranking to obtain the final candidates. Looks a little bit like this. So we ask the LLM to look at the candidate against what we're trying to do. It will do two kinds of scoring. One is a numeric scoring from 0 to 10, and the other one is a categorical evaluation. And then we take the combination of these over multiple prompts and average them. And then we have apply a threshold to get a final set of rankings. So there is some reasoning by the language model to assess the quality of the match between what is the query and the set of concepts that are retrieved from the database. Okay, so then when we have these, when we compare our results, our tool is able to identify correctly the concepts associated with the 3 cases that indicated to you, as opposed to the other models that don't have these kinds of filtering and re-ranking steps. And so the performance is reasonably good in the sense that the candidates that the curators see are of much higher quality than if you didn't do this approach. And more importantly, it certainly helps them, I think, to decompose these complex clinical variables into a set of components that individually can describe that component itself. So we do fairly well across using both the open source language models like Llama 3.1 as well as the commercial language models like GPT-4, and certainly helps our curators do their work. Okay, so this represents CDMapper as a new kind of retrieval augmented framework that is specifically intended to be used for clinical data standardization. It performs very well, certainly against the other methods that don't use these more sophisticated techniques, and in the end provides data that are going to be standardized descriptions of these clinical variables. Now, the next part that I want to talk to you about is some of our work that has part of the challenge that we have seen is in that construction of these more elaborate descriptions of our variables. It is often the case that none of the domain terminologies like SNOMED or any of the other ones have all of the vocabulary necessary to construct a meaning. And you kind of have to wonder why that is, right? And I think a large part of it is because they are really focused on particular representations, particular scenarios and concepts in the domain that they want to formalize. This means that they have a specialized terminology or vocabulary that isn't generally available to use for arbitrary descriptions. It's really going to be very specific, for instance, to the healthcare domain or to any particular situation that they are intended to be used for. So they do perform well as ontologies for that community and for the use cases that they're typically applied for. They're responsive to the needs of this type, sort of use cases that they have. But as soon as you move beyond that, you start to see where the boundaries lie. And so a critical distinction between domain ontologies is really this idea of the upper level ontologies or these foundational ontologies, which offer an overarching axiomatic framework for domain ontologies that would constrain the way that they think about the world and how they would represent it in a machine interpretable manner. Many ontologies and schemas don't use upper level ontologies, and that includes, healthcare standards such as SNOMED, or data schemas such as the Swiss Personalized Health Network, RDF schema. These are often driven by, indeed, these immediate and pragmatic needs that are driven either from the data or from the context in which they are thriving. And as a result, the lack of adherence to an upper level ontology leads to really inefficient representations. They will struggle to extend their domain ontology or schema to new use cases that weren't originally considered, and that they will have to create a proliferation. There will be a proliferation of predicates or relations that are not necessarily compatible or even defined against the ones that were previously shown. And I think this is what yields now increasingly complicated, both cognitively complicated, and I think just in terms of the functions of finding the relevant relations, finding the relevant classes becomes increasingly difficult by the users. So let's take a look. So here's an example from SNOMED CT, which is a well-known ontology in medicine, and it covers all kinds of things, right? Diseases and symptoms, procedures, body structures, and so on. It has about 375,000 classes in the English language one, with 19 top-level classes and 246 properties that can be used to compose these expressions. So here's an example for myocardial infarction. Actually, its definition is inferred from its parent descriptions, which includes that it's a kind of myocardial necrosis, it's an ischemic heart disease, And from a description perspective, it has an associated morphology of an infarct and a finding site in the myocardium structure. So what we see is, again, even when you look at the top level structure, these 19 categories, many of them actually share attributes, right? So if you look at body structure, organism, pharmaceutical, biological products, specimen, these are all kinds of physical entities, right? But, and so the question is, do they have fundamentally different kinds of characteristics, or do they share something in common that, and when you look at each of the different categories, you will see kind of a specialization of their relations, specifically targeting that particular category, even though there's a fundamental semantic relation between the relations that are found from one category versus another category. So there's a missed opportunity for simplifying the vocabulary of relations in order to foster reusability of a basic set of relations. Similarly, in the SPHN RDF schema, it's an effort and it's a national initiative to foster the reuse of health data for research purposes. Involves a number of different clinical care providers in Switzerland, and basically defines a schema by which these hospitals and data providers will structure their information in order to share it with the researchers, right? So all of the hospitals are working together. And there's a whole technical interoperability framework that they have developed. There's great documentation, sort of defined schemas and standards and so on, and an element of governance that goes with this. So it's an enormous effort by our colleagues in Switzerland. The schema, which is again an RDF schema, but it uses OWL constructs, comprises 66,000 classes and almost 1 million axioms involving 19 external vocabularies. So they've done an incredible job of trying to pull additional vocabularies that are needed to describe the data that they are encountering. I think this is really valuable. And so here's an example of one part of the schema which pertains to diagnosis. You'll see in this diagnosis, they have a number of different relations to different kinds of things. So diagnosis has, you can use a predicate called has subject age to relate the age of an individual to the diagnosis at the time of the diagnosis. You can associate the diagnosis with a code drawn from one of the other external vocabularies. They can be associated with the patient through this a relation called subject pseudo-identifier, and it can be related to a parent administrative process, which is basically the healthcare encounter, which is called the administrative case. So you can see this schema, right, is really different. The vocabulary that is used here is really different than what we see in SNOMED, right? I mean, there's no correspondence between the data elements and also in the relations itself, right? But they still are talking about the same kind of domain. So in foundation ontologies, one of the problems we say, well, foundation ontologies provide us with a set of parent categories, upper level categories that we can potentially reuse across the different domains, as well as a set of relations that help us construct these meanings, right, to create definitions. The problem with upper level ontologies or foundation ontologies have largely been that you really need a background in both logic and philosophy in order to understand the intention of these categories and the relations and how to construct them in the language of implementation, right? So whether that's OWL or something like that, takes quite a bit of expertise to do so. The other problem is that these upper level ontologies often have unfamiliar or very technical labels, and things like continuant or endurant or specifically dependent continuant, which are really valuable to avoid the overload of of labels that we might see. So object and process and things like that. You would think that that might be really straightforward, but different people will have different interpretations of that. And using that specialized vocabulary certainly is going to help say, well, I have a very distinct meaning about this, and you need to understand it before you apply it. But the counter to that is it's going to be really difficult to grasp and correctly apply by non-experts, right? So we often see, even when people do mappings to upper level ontologies, their mappings are not they're not accurate and they're not correct. And it's difficult for them to assess that this is the case. There's also variable coverage in upper-level ontologies. They have very distinct areas in which they focus on. They might ignore completely other parts. They might have some element of being underrepresented or even over-constrained in some areas. For instance, BFO and Dolce focus on particulars, and only BFO has time-indexed relations in their common logic implementation. Immaterial barriers are not possible in BFO, and then BFO, GFO, and Dolce don't offer any data relations out of the box. So, you have like this different set of focus by the developers in order to guide, like, again, the conceptualization and formalization of the domain, which is enormously valuable, but they are not really well aligned to each other either. Now, another issue is that, I think many of us in this community have spent lots of time trying to, to understand the basic formal ontology and to apply it in our work. And we would all agree that it takes considerable effort to, to really untangle what these concepts are and how to compose descriptions and things like that. And in a study that was performed some time ago, our colleagues asked experts in the basic formal ontology to classify 46 commonly known entities from the domain of travel. And there was a relatively low, I think, inter-annotator agreement or inter-rater agreement of 0.5. And it's worth noting that the degree of classification consistency correlated with the frequency of the respective BFO classes that are used in practice. So basically, the further down you go into the upper level ontology, the less likely people are going to agree that that's the right category. All right, so what do we want out of an upper level ontology? I would argue that we want something that is going to be cognitively accessible in the sense that, one, it's relatively small. This contains a small set of disjoint classes and a minimal set of constrained relations that can be used across all the different domains that we might have, that we might be interested in. It ought to be, I think, a glue between the different upper level ontologies in terms of the core components that are kind of essential for most different kinds of domain representation. While remaining accessible to the domain experts, it should be accessible to users with little or no training in formal ontology through friendly labeling and this minimalist design. They should provide the building blocks to construct complex and machine-readable class expressions. And they should foster interoperability by providing a common semantic foundation, which are strengthened by ontology design patterns. So basically something that sits on top of the basic classes and relations that you have so that domain experts can implement standard, I guess, or very reoccurring kinds of scenarios that they want to represent the knowledge for. And then to be used as a basis also for the development of schemas, to guide the development of schemas so that we have more interoperable schemas and to do data validation using these upper level ontologies. So what we have done is developed a new upper level ontology. We call it the Simplified Upper Level Ontology, or SULO. And it takes this minimalist approach to guide the alignment, formalization, and reusability of both upper level ontologies, domain ontologies, and schemas. And we're trying to balance the former rigor of ontology with the simplicity and practical usability of data and knowledge representation. Basically, we did this following the typical NEON methodology. The group of us were experts in the biomedical domain and gathered use cases and requirements from these use cases. We challenged to identify key categories or classes that are needed to represent these use cases and the basic relations that hold between them. To align these with the standards, the healthcare standards, and other upper level ontologies, and to do an iterative development and validation of our approach using case examples. And also have lots of beer while we're doing it. Here is the SULO ontology, so it comprises of 17 classes. At the top level, we distinguish between two main categories, processes and objects. Objects are then split between spatial objects and features. So these would be in the BFO considered to be more of the union of specifically dependent continuance, and realizables, I guess, generically, specifically, dependent continuance. Features comprise of rules and qualities, capabilities, and information objects. And interestingly enough, we go further than you would typically see in the basic form ontology and define categories that are typically used in domain knowledge representation, including collections or sets and quantities, as well as being able to measure time. That is the measurement of time in the units of various measurements in order to capture the temporal aspects of both processes and in data collection. So Sulo has fewer top-level categories compared to the upper-level ontologies. You can see this here just visually between Sulo, the basic form ontology, Dolce, GFO, and GUFO and GFO. And it's important to note that Sulo captures a subset of these categories, right? And again, our goal is to have more the core set of categories that are needed as opposed to an expansive set with elaborate theories around space and time, change, and so on and so forth. Sulo has 18 object properties, so nine object properties and 9 inverses of those object properties, and 1 data property. So they capture the kind of basic components that you would typically see. You have containment, spatial and temporal containment, parthood, mereological relations, temporal associations, and temporal ordering, participatory and attributive relations, information content relations of reference, and membership in sets. So yeah, now you can compare here visually the set of object relations. You can see it's substantively reduced from the basic form ontology and GFO and GUFO and Dolce. And kind of our premise here is that actually, if you look at some of the other ontologies, you have a lot of specialization of object properties that are perhaps a consequence of the manner in which they formalize them in the web ontology, using the web ontology language. But arguably, some of these do map very well to Sulo, and others are outside of what we cover. So Sulo, here's an overview diagram, and this was a bit part of our objective is to create an ontology that fits on a postcard. You can see all the classes and the classification, the taxonomic organization of the classes, as well as the relations on this. So the solid lines indicate the domain and range of properties, object properties that are defined, as well as the dotted lines show where the properties are used as restrictions. So for instance, in contrast to what we see in the basic form ontology, there is not a separate mereological relation for processes or endurance or continuance. In fact, it's just articulated as an expression, a class restriction on those categories to restrict them of that type. The other part that we do is we augment Sulo with a set of design patterns, ontology design patterns, and the idea here is to reduce the proliferation of data and object properties that we see by ontology developers and schema developers, to try to encourage them to reuse the subset of relations that we have already defined. So we have these 2 patterns, the solid pattern, which is focused on describing literal values, and the pro pattern, which is focused on describing role-based relations. So I'll give you an example here. The solid pattern makes use of Sulo's single functional data property called hasValue to assign a literal value to an information object. So instead of having an arbitrary relation such as hasTemperature or hasTemperature in Celsius, the design pattern uses hasValue, hasFeature refers to, and hasPart properties to, in conjunction with 2 externally defined classes such as temperature from Pato or Celsius from the unit ontology to construct this description. So there is a semantic correspondence between these. Again, these are kind of like complex object properties or complex data properties, and we can compose their meaning using the elementary relations that we have in the Sulo ontology. Similarly, for we see a lot of relations that would be like has agent, has patient, has subject, whatever it is. These are typically referring to the role that an individual plays in a particular circumstance. So the pro pattern is intended to represent the manner in which objects participate in processes through the specific roles in that particular context. And so here what we do is we relate a process to a role through the has participant relation, and that this role is, as a feature of some particular object. And by adding a role chain in the ontology, we can infer the participation of that downstream object, which is the holder of this role. So this helps, I think, to reduce the impulse to create new relations, but arguably just try to create or extend role hierarchies in order to articulate how is this object participating in a particular process. Yeah, so here's an example where we might have a healthcare encounter, which is a kind of pseudo process. It has two immediate participants, which are these roles, right? So there's the role of Alice as a patient, and there's role of Dr. Smith as the healthcare provider, and these are the features of these two individuals. And so when we ask the question from the knowledge graph, then we obtain an inference that both Alice and Dr. Smith are participants in this encounter. So the other part is that we want to do is to try to ground our domain ontologies using Solo. And that is what we want, is to not only provide a formal semantic to the categories, but also to the relations. And many of the relations that are in there, SNOMED has like hundreds of relations. And some of them are very complex. That is to say, they sort of span they don't directly refer to properties or immediate attributes of those objects, but they kind of are shortcuts, let's say, through the semantic space. But what we want to do is, after having done a mapping of SNOMED classes and relations to the pseudo classes and object properties, we can construct descriptions of these entities in a more generic way. That is, we don't need to introduce new relations. We can reuse the set that we have. So if you take a class like we have in SNOMED, fracture of femur, this is termed a disease or disorder. It has in SNOMED the role group or attribute, which is this associated morphology of a fracture and a finding site of the bone structure of femur. So you can see in the structure of the description, it makes use of this role group, which is this kind of associative construction, and then two kind of qualifiers. But the description that we would use in SUL would follow this, right? It would be that the disease has a part, which is a process in which occurs in the bone structure of the femur, which has this morphologic abnormality of being fractured, right? And so what we try to do then is regularize this description of situations or scenarios or terms that we have in the domain to some kind of regular structure. Similarly, in SPHN, we see a lot of these has something kinds of object and data properties. And interestingly enough, as a use case in our project, in the IDAVA project, we encountered the case where the specification itself changed from one version to another, that the set of properties, object properties changed, and also the classes changed in that time. So it's very brittle, right? If you have such a tight linking of your data to your schema, the moment you want to change it up, you're going to break everything. And so what happened was in the 2023 version of SPHN, they had these properties like has admission date time, right? Which was to indicate the date time of an admission process. And that was replaced later on in the 2025 version with a has admission as an object property that instantiated an admission class in which the property was no longer has admission date time, but was has date time. Okay, so both the whole structure of that graph changed dramatically. But whether you're using the 2023 version or the 2025 version, it has a corresponding identical representation in Sulo. That is to say that an admission is a process that is part of the administrative case. And as a process, it can be, we can associate the temporal aspect of it as the time at which that process occurs with the at time predicate. And we can capture the value with the has value predicate. So in this sense, whether you're using the 2023 version or 2025 version, the representation, the Sulo-based representation is exactly the same. Okay, so Sulo, we compared Sulo with other ontologies like the basic form ontology, and you can see a lot of similarities for you that are familiar with that. They share this top level binary division of process and object, or current and continuant. The Sulo's object class simplifies the GDC SDC IC. It contains information objects such as quantity, collection, time that BFO doesn't. Sulo has a data property, but BFO doesn't. But BFO has spatial and temporal regions, and part of their definitions depends on these things. They have theories about ontology theories about these things, and Sulo doesn't. It doesn't say anything about it, doesn't exclude them, but it just simplifies the representation to not have to consider them in the first place. Yeah, so Sulo takes a minimalistic approach to the upper level formulation, ontology formulation that balances this formal rigor with the simplicity and practical usability. It's a work in progress, and we are eager to hear from you your thoughts about this. You're welcome to reach out to us and share with us your opinion about that. I share you the link to the GitHub project. We've not made a full comparison of all the upper level ontology classes, relations, and their application. But I think it's a good starting point as a kind of like simple starting point for most use cases that are largely compatible with other upper level ontologies. Although we do intend to see, will this representation be a lot easier to use for end users than others? Okay, so actually, in the last few minutes, I'm just going to reflect a little bit. Last year, I gave this keynote at Voice on the future of health AI is our knowledge infrastructure up to the task, and I had a slide which was, if only we could map health data standards to upper level ontologies. And I'm glad that we've taken some steps, I think, to work on this problem. But really, the motivation is not just to have, like a semantic grounding of health data standards to ontologies. I mean, what as a data scientist, my real interest is whether the data comes in FHIR format or OMOP or SNOMED or SPHN or whatever format it is, I don't want to care too much. I mean, I want to ask my questions potentially with any of the terminology that are expressed in any of these data formats and also the vocabularies they use and return all the correct answers for those questions. But key to this approach is that given the heterogeneity in all the different standards, it's essential that we have some kind of mapping, some kind of correspondence or interoperability between our healthcare standards. And the only way to really do it is if we have a correspondence that is through an intermediary, such as Sulo, that can express their concepts and relations in other terms so that we can find compatible terms and expressions across these different standards. And I think that's a bit at the heart of the work here, because what we really want to do is if I have FHIR data, I want to be able to convert it into this Sulo-compliant representation in a bidirectional manner, right? And that from the Sulo-compliant representation, I can push it out to another standard, like for instance, OMOP or what have you. And so this is kind of work in progress, but our colleagues that work on the SHEX shape expressions technologies, they have developed a new mapping language called SHEXMap, which allows us to express the compatibility or the correspondence between data elements and data values in order to construct this bidirectional transformation between these different schemas. And I think that's a very important development. And it's important that you recognize that it's not sufficient to only have binary or pairwise mappings, but actually the mappings, the semantics of the data we collect and the concepts we create is multifactorial, and it's kind of a graph-based representation that gives us the better context of full meaning of these data and our concepts. So we need to have these more expressive languages to construct correspondences between them. Yeah. Okay, so already in a couple of weeks' time, we'll have a workshop at IHD to work with healthcare standards developers to see whether they can do this cognitive mapping of SULO to their own healthcare standards, and then to see if they can come up with shared representations of what are otherwise lexically and potentially conceptually different things. Can they find correspondence between the standards that are represented there? Okay, so I saw Mark's talk with a little bit of amusement as he was complaining about how his advisory board was telling him that ontologies are late game. It's kind of over for ontologies, and maybe we need something else. And he had put up this slide, which was, what do we do to quell these concerns? Acknowledge that ontology engineering is hard, but good tools can make it easier. I think that's certainly the case, as I showed you with CDE Mapper. Good tools are going to help our workers implement data interoperability much better, as well as design ontologies, I think, in a much better quality. Educate people about the importance of standards for data management, accept that the important standards come in forms that are not ontological, but I would add that we have to continue our work in aligning standards to semantically interoperable representations. And I think it has to go beyond just simple mappings, but far more richer representations are needed, and it has to be accessible by our standards developers. Okay, so in summary, yeah, I hope that in this talk I was able to show you that language models are really powerful technologies that can assist us in the work of structuring and standardizing scientific data. There are many other talks actually in the conference that also are exploring the use of language models for ontology-based purposes, and I think that's an exciting development. That simpler upper-level ontologies, such as SULO, may be able to help standards developers construct compatible representations. I think that's the key part. It's not that we have to have everybody aligned to a single standard, it's that we need to have interoperability between the standards, right? And that will help them keep their maintenance lower and have opportunities for expansion that are compatible with other models. And that new efforts are needed to capture and share these complex mappings in a fair manner. And I think that's going to be a bit the focus of the work over the next year. And I think if you're interested in this topic, I would love to hear from you, and maybe we can collaborate on it. Yeah, so thank you for your attention. Happy to take some questions.